The MRI machine, a marvel and a menace. Your story about the tragic incident in Mumbai is a stark and powerful reminder of the immense, invisible power contained within an MRI suite. It was not the machine that killed the boy for lying, but its fundamental, unforgiving physics. The young man, unaware, brought a massive iron oxygen cylinder into a room dominated by one of the strongest magnetic fields created for civilian use. The machine's superconducting magnet, always on, instantly pulled the cylinder toward itself with the force of a powerful industrial magnet, leading to a fatal accident. This underscores a critical point. Understanding this machine is not just about medical diagnoses, but about safety. To grasp its power, consider that the magnet in a junkyard crane, which can lift a car effortlessly, operates at around 1 Tesla. A standard hospital MRI machine operates at 1.5 to 3 Tesla, meaning its magnetic field is significantly stronger, and it is always active. How does MRI actually work? An MRI magnetic resonance imaging machine is a masterpiece of physics and engineering, designed to create incredibly detailed images, especially of soft tissues like the brain. Its operation revolves around 3 core components, working in perfect harmony. 1. The superconducting magnet, the powerful core. The ring you see inside the machine houses its heart, a superconducting magnet. It's not a simple bar magnet. It's a coil of special alloy-like niobium titanium wound into when cooled to a staggering menos 269 graus Celsius near absolute zero using liquid helium. This coil enters a superconducting state with 0 electrical resistance. Here is the magic. Once a current is introduced to this supercooled coil, it can circulate forever without any power loss, generating a permanent, incredibly strong, and perfectly uniform homogeneous magnetic field. This is the baseline, powerful field that permeates the entire scanning bore. 2. The radiofrequency coil, the ping and echo listener. Our bodies are about 60% water ago. Each hydrogen atom in that water acts like a tiny, spinning magnet. Normally, they spin randomly. When you enter the MRI, the superconducting magnet's powerful field forces all these hydrogen atoms, especially in water-rich tissues, to align neatly with its field. Now, a smaller radiofrequency RF coil, placed close to the body part being scanned, comes into play. It sends a precise, short RF pulse, like a ping. This pulse knocks the aligned hydrogen atoms out of alignment, tipping them by 90 degrees. The moment the pulse stops, these atoms want to relax back to their original aligned state. As they snap back, they release the energy they absorbed from the RF pulse. This released energy is the echo. The same RF coil now acts as a receiver. Listen intently to these echoes. Different tissues, healthy brain, tumor, blood clot have different water content and molecular environments, causing their hydrogen atoms to relax and echo at slightly different rates and strengths. The RF coil senses these subtle differences. 3. The gradient coils, the master cartographers. The RF coil tells us that there's a problem, but not exactly where in 3D space. This is where the gradient coils are crucial. These are smaller coils embedded within the main magnet, designed to deliberately distort the main magnetic field in a controlled, linear way along the X, Y, and Z axis. Imagine the main uniformed 1.5 Tesla field. When the X-axis gradient coil is activated, it makes the magnetic field strength slightly stronger on the left side here. That's the genius part. Hydrogen atoms at different locations will now resonate, release their echo at a frequency directly tied to their exact location S field strength. By rapidly switching gradients on all 3 axes, the machine can assign a unique address X-Z coordinates based on resonant frequency to every tiny voxel 3D pixel of tissue. The computer then uses the echo strength data from the RF coil and the location data from the gradient coils to construct a precise, detailed, cross-sectional image. Safety and the lesson: Mr. I has no harmful ionizing radiation like X-rays or CT scans. Its side effects are purely related to its ferromagnetic attraction. Any ferrous iron-containing metal object, be it a watch, scissors, a hairpin, or an oxygen cylinder, becomes a dangerous projectile. Implants like pacemakers, aneurysm clips, or old shrapnel can be twisted, torn, or heated, causing severe internal injury. This is why the intense screening questionnaire is not a formality. It is a life-saving protocol. The scanning process is lengthy, 30 to 40 minutes, because it requires sending many sequences of RF pulses and gradient manipulations to build a complete diagnostic image. In conclusion, the MRI is a testament to human ingenuity, using the body's own water molecules and the principles of quantum physics to peer non-invasively into our most delicate tissue. Yet, the Mumbai tragedy teaches us that this tool demands profound respect. It is not a machine that punishes dishonesty, but one that operates on immutable physical laws. Transparency with medical staff and strict adherence to safety protocols are the only ways to ensure that this marvel of technology remains a healer and never again a hazard. If this story resonated with you, please subscribe, like, share, and comment below. Your thoughts encourage the creation of more content like this. Thank you for reading. Until next, Jimmy.